en esta ocasión, en este día 25 de julio de 2024. Sean todos bienvenidos a esta nueva emisión de este ciclo de conferencias que transmite Geotem Ingeniería para todos ustedes. Yo soy Leonardo Veras y conmigo el día de hoy me acompaña Elío Ramírez, quien es el encargado de monitoreo sísmico en Geotem, junto con otros compañeros de la compañía que también colaboran y se encargan de esta actividad, y que es precisamente el tema que tenemos para ustedes el día de hoy. Eliu, te doy la bienvenida por primera vez, sí, creo, a XPERTS.
Sí, así es, Leo. Muchas gracias. Pues emocionado de estar en este programa de Geotem, donde se abarcan diferentes temas, son temas diversos. Hoy nos toca abordar el tema de monitoreo estructural, dentro de otros tópicos, con un invitado muy especial para nosotros, un integrante prácticamente de la familia Geotem. Pues estoy muy emocionado de estar aquí contigo, con los que nos están escuchando, y con Mauro.
Muchas gracias, muchas gracias. Y efectivamente, quiero comentarles acerca de nuestro invitado el día de hoy, que es el ingeniero Mauro Mariotti, de la empresa SARA, Electronic Instruments. Él es el director de la empresa, y cuando le platicamos a Mauro acerca de cómo presentarlo y que nos hiciera llegar su semblanza para dar sus créditos relacionados con su profesionalismo y su carrera profesional, nos dijo que simplemente les dijéramos que él es un ingeniero electrónico y que es un experto porque se ha dedicado prácticamente su vida a la instrumentación sísmica. Así es que simplemente con esas palabras y esa introducción queremos darle la bienvenida a Mauro. Mauro, bienvenido a XPERTS y muchas gracias por estar aquí con nosotros en esta conferencia el día de hoy. Quiero decirles que la conferencia hoy tiene una particularidad. Mauro está en Italia, va a estar con nosotros de manera virtual, y la conferencia la va a platicar en inglés para todos nosotros. Aquí detrás de cámaras está nuestro querido Giovanni Mendoza, que nos está apoyando en los controles, y él ya tiene habilitado la traducción simultánea, que ustedes podrán ir leyendo en sus pantallas. No obstante, queremos que nos den sus comentarios, y si hay cualquier cosa que no se llegue a entender, que nosotros los podamos asistir y podamos ayudarles a que se entienda completamente toda la conferencia. Asimismo, Mauro nos ha pedido que si hay alguna duda o ustedes quieren intervenir con alguna pregunta en medio de la conferencia, que también lo podamos hacer para que se haga de una manera mucho más dinámica y no haya ningún tema que se pase malentendido, ¿de acuerdo? Entonces, quiero cederle la palabra a Mauro. Mauro, de nuevo, bienvenido y muchas gracias por acompañarnos aquí en esta conferencia de XPERTS. Adelante, Mauro. Creo que estamos teniendo un problemita de conexión con Mauro. Ahorita lo solucionamos. Lo teníamos aquí al principio de la transmisión, pero en este momento no está. Bueno, quiero comentarles que Mauro nos va a platicar sobre instrumentación sísmica con equipos SARA, que es precisamente, digamos, los instrumentos de la cual él es director de esta compañía. Instrumentación sísmica con equipos SARA de alto desempeño. Justo estamos teniendo unos tiempos en el que el mercado se pone muy competitivo, en el que tenemos bueno, parece que se va a volver a...
Sí, se desconectó, ahorita se vuelve a conectar.
Muy bien, mientras les voy platicando, el mercado se ha puesto muy competitivo y de ahí que creímos de la importancia de traerles a todos ustedes este tema con nuestro querido Mauro Mariotti desde Italia. Mauro, ¿nos puedes escuchar? No sé si nos está escuchando.
Mauro, can you hear us?
Bien, ¿sí nos escuchan?
Hola, buenos días a todos, Mauro, Julio.
Okay, we can hear you, Mauro. Can you speak, please?
Muy bien, en cuanto...
It's okay, Mauro. You can speak now if you want.
Okay, the introduction has been done. Should I start?
Yes, okay.
Yes, okay, let's start.
Okay. Start the presentation, just a moment. Can you hear me? It's impossible for me to share the screen in this moment.
Okay, give me a minute.
Give me a minute.
Giovanni's
gonna fix it briefly.
But can you talk
about
SARA,
like
as your company?
as your company?
Yes, I would prefer to use the presentation, but
Sure.
anyway, I am Mauro Mariotti. I am the director of SARA Electronic Instruments, and we manufacture electronic devices for seismology and soil exploration, basically. So I am very glad to have been invited by Geotem for making this presentation. And we had some technical problem on maybe on the operating system. I don't know what is going on, but I wanted to present to you an introduction of our company and what we do. I don't know if Geotem can allow me to share the presentation, or maybe I have to reset my connection because it's not allowed to me in this moment.
Mauro, can you try again to share your screen, please?
Yes, one moment. No, not possible to share. Now I try to share the whole screen.
Okay.
No, not allow it. I think they have to reboot my computer. Yes, I don't think it's possible to. Oh, something happened. No. Yes. Can you see the screen?
No, we can't see the screen.
You cannot see the screen?
I can't see the screen.
Okay, perfect. So we are a company which we're based in Italy, and we manufacture since 2004, manufacture seismic instrumentation. And we, until that time, we manufactured over.
Sorry, Mauri, we can't
Yep.
we can't see your screen. We are not seeing nothing in this moment. If you want to reboot your computer, we can wait about 2 minutes, no problem. And Leonardo and I can speak about
Yes,
las
please.
formas mexicanas de construcción. Yes, Mauro, don't worry.
El tema técnico, platiquemos un poquito acerca de su presentación el día de hoy, lo que ustedes van a escuchar acerca de lo que él va a platicar. Nos va a platicar un poco acerca de la diferencia entre lo que es la señal, lo que es el ruido y lo que es el ruido ambiental. También nos va a platicar del modelo de ruido de Petersons. Nos va a platicar acerca de los diferentes sensores para piso con que cuenta su compañía, desde geófonos hasta sensores FBA y los recientemente que se han ido desarrollando los sensores MEMS, que son a base de tarjetas electrónicas.
Así es, Leo. Es lo que nos va a platicar hoy Mauro, y también tenemos conectado al ingeniero Carlos Pita de La Paz. Ingeniero, buenos días. Buenas tardes ya.
Buenas tardes ya.
Adelante, Carlos.
Adelante, Carlos. Hola. Bueno, pues muchas gracias por la invitación y a todos los que nos acompañan por estos medios. Sobre todo, agradecimiento a Mauro Mariotti por, digamos, asistir a esta reunión donde nos va a platicar sobre las tecnologías de SARA. Nosotros en México pues representamos a SARA y afortunadamente tenemos un potencial de ventas muy bueno, donde la tecnología de SARA se ha vuelto un aliado tecnológico en las empresas de exploración, sobre todo en el área de la salud estructural de edificaciones, en el conocimiento del subsuelo, en fin, a través de métodos como downhole, más W, todo lo que implica las mediciones de sísmica terrestre e incluso también a nivel de las variantes, ya sea de refracción sísmica o reflexión sísmica. Es una tecnología bastante innovadora, sobre todo en la parte tecnológica. El peso, los equipos son ligeros, permite viajar con ellos en avión incluso, muy cómodo para el traslado de estos equipos, y eso hace que los ingenieros de exploración estén muy contentos con esas tecnologías. Gracias.
Gracias, Carlos. Vamos a seguir esperando que Mauro resuelva el tema técnico con su computadora. Mientras seguimos platicando acerca de lo que nos va él a platicar el día de hoy. Otro tema que va a abordar es acerca de lo que se llama Big Mass Block, por su título en inglés, que son digamos presentaciones de videos en banda ancha. También acerca de conexiones en tiempo real, que es algo muy importante para el monitoreo de estructuras y conocer información en tiempo real cuando sucede algún evento en las estructuras. Mauro, ¿estás por ahí de nuevo? Mauro, are you there? Bien, vamos a esperar que Mauro termine de conectarse y resolver el tema técnico. Vamos a hablar también, bueno, Mauro nos va a platicar acerca de la calidad de los datos cuando se hacen análisis de H entre B, los famosos análisis de los estudios de vibración ambiental. Y lo va a hacer, nos va a platicar cuando se usa un programa que ellos han desarrollado para estos tipos de análisis que se llama GeoExplorer. También la calidad de los datos en las señales de edificios, y se va a poner como ejemplo el metro de la Ciudad de México, usando también el programa GeoExplorer. También nos va a platicar acerca de los procesos, digamos, la deconvolución mediante procesos de desplazamiento con otro programa que también han desarrollado ellos, que se titula Seismos Survey.
Yes, Mauro, we can hear you.
Yes, Mauro.
Bien, y al final nos platicará también un poco acerca de la salud estructural.
Station, but it was not still working.
Bien, parece que ya tenemos a Mauro de regreso. Vamos a esperar que pueda compartirnos
Now I try
su presentación.
to recover from here. Can you hear me?
Sí.
Yes, we can hear you.
Yes.
Vamos a esperar que Mauro nos pueda compartir pantalla para mostrar su presentación y que nos pueda platicar de estos diferentes tópicos que hemos comentado. queremos comentar que Geotem es representante de la marca SARA en México.
Okay.
Muy bien.
Okay, can you see my screen?
Yes, we can see your screen now, Mauro.
Somebody can give my feedback on the screen, please.
Yes, we
Yes, Mauro.
we can see your screen, Mauro.
Bien, pues adelante. Go ahead, Mauro. Oh,
Okay, so seems that I am finally online. So my presentation is in this moment regarding our company. At the beginning, I was saying that no, this is the wrong screen. I'm really sorry. I'm really sorry. It seems that okay. So I hope it will work now. Our company, I was saying, that is on the market for seismology since 2004. So we have now about 20 years of experience. And we have manufactured in this moment over 7,000 seismic units with seismic recorder, transducers, force balance accelerometers, put in service thousands and thousands geophones, also borehole sensors and exploration seismographs. Also, we develop and distribute some software regarding monitoring and soil exploration. One of our major installation is accomplished in Turkey. In Turkey, the civil defense has a large number of our force balance accelerometer, named ACEBOX, with their only one sensor with digitizer and recorder and sensors. So they transmit data in real time to the Civil Defense Department for assessing the seismic risk in Turkey. You know, Turkey is a very highly seismic country with a lot of earthquakes and also, unfortunately, a lot of damage in the last years. So we help to assess the seismic hazard in this country and in many other countries, but Turkey probably is the country with more equipment from us. We provide tools for seismic, not only for strong motion, but also for weak motion and microseismic. We provide ultra-high resolution sensors and recorders for example, microseismic application, which is mostly used in the mining application. So for gas storage plants and other application where very small earthquakes have to be detected in a limited area. We also manufacture a hybrid sensor, including velocity meter and seismometer, velocity meter and accelerometer, broadband seismometer, and other equipment. This is one of the typical installation with the cabinet with maybe solar panel, large batteries, and seismometer outside. Another type of application we have is a borehole sensors. So we have a borehole carrier which has a hole lock, so it can be locked inside borehole. So you can put your sensor in any highness on the borehole and receive the seismic signal from not from the surface but below the surface using holes digged in the ground. This is another sensor, a type of sensor. It's a broadband sensor we deployed in Turkey again for a gas storage plant. And this is a part of a larger network, including 3 seismometers, broadband seismometer onshore, and also 4 offshore. I will show you later also a video regarding this. This is an installation of a broadband sensor for the Italian national network. It is in a borehole with a depth of 165 meters. It is, this is interesting because this equipment is a hybrid, because it has in the same capsule, it has both broadband sensor and force balance accelerometer. So the dynamic range of this type of equipment is very, very high. This is another broadband installation for geothermal company. It's, in this case, it's a HERA. It's a part of the geothermal field exploiting in North Italy near Ferrara. This is another installation making borehole. This was an interesting installation we achieved with a borehole with a depth of 285 meters. It included 6 capsules. They working in the same hole using digital transmission over a bus, using a system we call digital array. Each one of these 6 capsules that you see on the lying on the ground before the installation contains a digitizer, 3 velocity meters, and they are connected together to the surface recorder. In this case, you can see some signals recorded by the 6 capsules deployed at this depth, this different depth. And as you can see, the capsule can detect, because the digitizing is made very near to the sensor, they can detect a very weak signal. This signal, which are fully correlated for all the capsules in this borehole, has an amplitude of about 200 nanometers. This signal is corrected in displacement. And the signal, the peak between these peaks, the time between these peaks about 3 seconds. So we can very well detect even low frequency than the eigenfrequency of the sensor. This is another type of equipment we produce. It's named Wellbox and Wellbox Hybrid. The Wellbox is only one sensor. You can have a recorder and data transmission and synchronization and a seismometer inside the one box. It is now available on the 24, 26, or 32-bit version, and also with MEMS sensor inside. Sometimes we can also obtain a very high dynamic range, because you can detect a very weak motion, very weak signals, and strong signals, because the MEMS sensor will not eclipse when a larger signal happens, and so you can explore the whole range of vibrations, very weak and very strong. For a very weak motion and planetary seismology, we manufacture these 2 types of broadband sensor. One is an observatory grade, mostly used for seismic observation, teleseismic and far earthquakes, etc. And this one is a smaller one, which can be used also for soil exploration or spot installation in the field. Recently, we introduced a new digitizer. This digitizer can be used for both civil and on-field installation. This is for indoor installation inside frames, inside buildings, and this can be used outside, because this is a protection grade higher. This is more practical to be used inside buildings. We will show you later more application on this. And one of the most important devices that we manufacture and also deploy and use in many applications, and also many clients are appreciating, is our force balance accelerometer. It is available in that 1G, 2G, or 4G and 100 or 200 hertz. And it can be supplied in a triaxial, biaxial, or monoaxial unit, and also in borehole unit. So if you want to record earthquake strong motion inside the below the ground, you can use also this type of installation, this type of housing to be used in the borehole. Then we have a series of equipment, because of course you can monitor the earthquake as much as you want, but the best way to protect the people from the earthquakes is to explore the soil and have a good design of the buildings before the construction. So we provide tools for soil exploration to comply the building codes. Building codes in Italy we have rather strict, and also many other countries like Mexico, like Chile, are putting in operation building codes to avoid to build maybe buildings in a bad condition, in a bad soil. So you have to know and analyze the soil property before you design, even before you design a building. And we manufacture not only exploration seismograph like Doremi, it's a multi-channel modular seismograph, and not only the GeoBox, which is a very special tool for Nakamura. It is one of the best instruments available on the market for this, very practical and cost effective. And they work very well also thanks to powerful software for both managing on the field, because both Doremi and GeoBox are the only instruments that we know, at least we know that are in the market. They have a software, a managing software capable to check the data quality on the field. So you don't need to go back to the office and make the analysis of the data, because you can check the data quality on the field during the data acquisition. So even you give shots for MASW survey or for HVSR survey, the software gives you the confidence that you are getting the data correctly just a minute after you are on the field. And then we have the processing software suite to analyze the data collected on the field. We have a quite extensive tool set for soil exploration, for refraction, MASW, reflection, HVSR, vibration monitoring, downhole processing. These are some screenshots of our HVSR analysis software, and this one is our software for MASW. All these software are very interactive, allowing the user to make the proper choices during the analysis, which for both HVSR and MASW are not trivial. So it's important for the user to have the full control in what is going on for the analysis and avoid mistakes. Downhole is also a processing software for downhole, which is one of the most direct exploration methodology for the famous VS30 calculation. Refraction for standard classic refraction analysis. And I can also announce that probably in the next month, or maybe around the beginning of September, we will release also the tomography for this application. So refraction, not only as a standard refraction, but also as a tomography processing. MASW is another interesting application we have as a processing, developed by an Italian geologist, Italian geophysicist, which cooperate. And he helped us to develop this interesting tool, which can give vertical profiles with the interesting feature of the proportion of depth length is about 1:1. So if you have a length of seismic line, let's say 50 meters of seismic line, you can mostly get almost 50 meters of depth investigation, which is one of the best ratio you can get for the VS30 or VSX depth calculation. And this is another interesting tool which is generating interesting in the last period. It's a kind of water search methodology. Water search methodology, which allow you to find possible potential aquifer, examining the scattering of the reflected waves. So using a very small, as you can see in the picture here, very small deployment of geophones, you can reach depth and analyze the depth of hundreds of meters using even small energy. It is sound strange, I understand. So we invite you to ask us more information, and we can demonstrate and we can provide you some examples. And there are more and more geophysicists which are using this method in Italy, and they are very happy. And then we have a software, a full set of software to provide the permanent real-time monitor, 24 hours per day, 7 days per week, and for recording, analyzing, streaming, relaying of seismic signal. This software, SeismoWin, can be used for both earthquake monitoring, but also to collect data for structure health monitoring. So we now finalizing these two software, so exploration and monitoring, and then in the next year we will start the development of also analyzing software suite for structure health monitoring. We now cover all the monitoring for structure health, and in the next year, most probably, we will demonstrate or will show, we display the new software for the structure health assessment, structure health calculation. This is one of the screenshots for the earthquake monitoring. So we have the streams, and we have calculation of the networks, to design networks on the field. And this is for the earthquake location, and also performing the calculation of epicenter, hypocenter, focal mechanism, etc. So now we give a little overview of what we are doing. So for building structure health monitoring, our equipment can be successfully used for this application. And this is one of the examples of the installation in a 15 floors building in Italy, Ascoli Piceno. In Italy, especially in our area, we don't have many very high-rise buildings, but especially in our area, we have a quite strong earthquake time to time. About every 10 years, we have an earthquake, major earthquake. So it's very important to develop this type of applications, and also make people understand that monitoring, especially big buildings, it's important to relieve and to mitigate the risk against earthquakes. In this case, this building has been monitored with 9 accelerometers, 3 on the base, 3 on the third floor, and 3 on the top floor. Later, maybe I can have the occasion to show you also some scheme of this type of monitoring system. This is one monitoring system over a bridge, using because this bridge was very volatile, and so we used simple MEMS-based accelerometer, like ShakeBot is one of our solutions. And you can see also there is the possibility to see the eigenfrequency, I mean the frequency mode of oscillation of the bridge. Another application we had made in the past years is from the Politecnico di Milano. They purchased from us an equipment that has been installed on the cathedral in Milan. And in this cathedral has been installed 36 geophones. Instead of using force balance accelerometer or MEMS accelerometer, geophones has been selected because it's a very stiff structure. It's very tall, but also very stiff because made in old materials like not concrete or steel. It's made in granite and stones, so it's very stiff. And the Professor Carmelo Gentile has published several papers regarding this experience. And they are very happy because they are detecting a very weak signal even on this big building. This is another application we had on the bridge, and this bridge is made of steel in the south of Italy. In this case, the Università Politecnica delle Marche, Professor Fabrizio Gara, they asked us to provide monitoring system which has been made of 5 temperatures and 5 thermometers on the asphalt and on the structure, meteorological station, and also 8 load cell which detect the tension of the cord of this bridge, and a total of 13 accelerometers, also geophones and extensimeter. This is part of the installation, the central recorder. And this is interesting because you can see these signals. This signal comes from the cord. In this point of the cord, 8 of all the cords, not all, but 8 of them, has been equipped with a strain gauge. So the strain gauge measures the tension of the cord. And the tension is proportional to the weight that the bridge in this moment is carrying on. And it's interesting that we used a methodology to do not measure the tension of the cord statically. So making few measurements per minute or something like that. But we installed a recorder, dynamic recorder. And so you can see that where the car is passing by over the bridge, the tension varies quickly. So the monitoring system can measure the weight, the instant weight each cord is sustaining. And also there are some weakling, there are some signals you can see smaller, which are the cord with the tension of the cord changes during time very quickly. So it's a kind of modal analysis of the cord itself using its own tension. This is something interesting that can be maybe implemented in the future, even by other in other bridges or in other installations. This is another example of bridge monitoring for dynamic monitoring. In this case, we are using geophones with a portable system, so to make quick analysis of the bridge. This is another installation made in Turkey. This is the Ziraat Bank. The Ziraat Bank is one of the most famous banks in Turkey, and this in the center is an historical building. This building has been is under restoration, so they removed almost everything from inside, and they are deploying a new structure to sustain the old historical outside walls. So in this case, the construction company wanted to be sure that anything of the construction or restoration of the building was damaging the building itself. So a number of ace box, a number of laser measurement, a number of accelerometer, a number of sensor has been put inside the structure, because this is the inside, to detect each instant of the restoration. So the data gather in real time to the control room, and when something is going wrong, maybe too much acceleration or something that starts to tilt a little bit, the building is, the activity is stopped and analyzed, etc. So everything is made under safety condition. So other applications in Turkey are for monitoring, for example, this Kamloka Tower. This Kamloka Tower is in Istanbul. It's very high. And inside we installed, I mean, not us, but our partner, our system integrator, installed a lot of our accelerometer. And also this one is a new installation of the recent months ago, which are tsunami warning on the Marmara Sea. The Candili University started the installation of accelerometer and meteo station and water level measurement. Everything is gathered by the same hour recorder. So we collect all the data from multi-parametric and send to the university. And so the university can detect the acceleration and maybe sudden water change in level water change if an earthquake happens, and put in correlation with wind speed, on rain, etc. And so avoid false alerting of eventual potential tsunami. It's a kind of tsunami warning. And now I will try to show you a video, possibly, because I told you that for a gas storage plant, we installed 4 borehole, sorry, not 4 borehole, 3 borehole sensors and 4 offshore broadband seismometer in the sea. So on the seabed, at about depth variable by 12 to 45 meters. Now I stop the sharing of this window and I try to share to you the video of this installation, hoping that nothing go wrong with my computer, because it seems that he is not cooperating too much today. Just a moment. Com'è? Che è successo?
Instalación de un equipo en el mar. Entonces es un video muy interesante, son instalaciones poco convencionales y sin duda va a ser muy enriquecedor lo que nos pueda platicar acerca de este video. En dado caso, para los que nos estén escuchando y viendo, si no pudiéramos escuchar el audio del video de Mauro, él estaría describiendo el mismo. Entonces estamos en espera de que él lo comparta, para que nos pueda hablar un poquito de su experiencia con esta instalación poco convencional.
Tengo entendido que esta instalación se hizo en Turquía. Para una compañía de gas. Entonces lo que vamos a ver es el video justo de esta instalación. Ahí está.
We can see now your video, Mauro. You can hear it, but you can describe it if you want.
It was off, sorry. We are in Marmara Sea, and I was saying that in the Bosphorus, where Istanbul is, very near to it, you know, there are very complex fault systems. And so there's a gas storage plant in the area, and I wanted to see if any activity of the gas storage plant is generating any activity, seismic activity, because it would be dangerous. So we developed this solution with a special marine cable and buoy to transmit the data. And the sensor is fixed on a concrete block for best coupling to the seabed, and then deployed with the help of a diver. So we put inside this big concrete block a seismometer, and the diver went down with a crane, deploying the sensor on the seabed. The sensor can sustain a tilt error of up to 5 degrees. So the diver go down with guiding the block. And the diver guiding the block down to the seabed. And after the concrete block is deployed, the leveling is checked. And if everything is okay, it was released. The block was released. The cable, the umbilical cord go up to the buoy that you will see now. The buoy has a solar panel, batteries, and everything to be connected with the internet, because there is a modem which transmits by internet in real time. So this is the view of the sea with the buoy. And just a few hours later, we recorded a nice earthquake from the 4 stations we deployed. So it was a very successful operation. And so with our partner in Turkey, Sentes.
Mauro, it's a very complex installation.
So meanwhile, I continue to my presentation. If somebody has questions, can also send to the questions to Geotem, and Geotem will revert question to me so I can answer. Meanwhile, I'll restart my presentation. Just a moment.
Podamos irlas desahogando desde ya. Yo tengo, Mauro, I have a question. This block of concrete, where you...
So, I don't speak Spanish.
So I hope that this translation that the ChatGPT, artificial intelligence, made, it could be understandable. All these things are possible only if we understand, if we understand very well the concept of the relationship between this signal and the noise. And we apply not only to the instrumentation, which is the key point of the recording vibration recording systems, but even to the specific case. So it's always a kind of challenge between the relationship of the signal and the noise. So what I'm going on to explain you now is it's something that I care very much, that we always care during our design of the instrumentation. When we deploy instrumentation, we always have to care regarding the capability of the instrument to gather to catch the signal, and the capability of the site to catch the signal of interest. And it will become more clear later in the next slides. So what is this diagram? This diagram is expressed in period. So these are the frequencies, or we can say the periods. And so we can here see that from high frequency on the left and low frequency on the right, because so long period, I mean, this is seconds, so short period and long period. You can see that these signals, these spectrums are calculated by John Peterson. John Peterson was a scientist who took a lot of seismic signal from a lot of seismic network, seismic station worldwide, collected them together, and found that there is no place on the Earth which has less signal than this curve. So this curve is always present as a level of signal on the Earth. This peak or this amplitude here in this point are generated by the ocean waves of the sea, oceans, which are put in motion by the wind and the currents, etc. And they push on the ground, and this motion of the waves are transmitted in the ground, in the crust, and travel for very far, for all the globe. And this pattern of frequency is detectable, and it is so-called ambient noise. So we call it ambient noise because it's something that is not related to any artificial signal, but is the signal coming from the Earth. And we can see this signal, for example, in this chart. What is this chart? This chart is expressed in this axis. We have the time, several days. Each number here is 1 day. So we have several days going on. Days. And we have here the frequencies. Okay, so 0.1, 001, 01, 1, 10, and over hertz oscillation. So we have the oscillation here and the time here. And what is happening? You can see a clear pattern with cyclically repeat. Okay, and this is the urban noise, which expresses itself at about from about 1 hertz and up to 20 hertz, 30 hertz. So you can see that you can recognize there are some days here, some you cannot see, or you can see lower signal. So this is a Sunday. During the Sunday, there is less signal. This is the Saturday. With the half of the day, it's more noisy, and then becomes more silent, similar to the Sunday. And then Monday, Tuesday, etc. So all these are days, 1, 2, 3, 4, 5, 6, 7 days. So these are cycles of the days of the ambient noise generated by the people, by us, by the car, activities, etc. But what is this pattern? This pattern which appears and maybe disappear, then appear again, disappear, etc., etc. What is this pattern? This pattern is generated by the atmospheric changes, by the perturbation of the changes in the atmosphere. And the atmosphere, the turbulences in the skies reflects on the sea, and the sea can become more agitated or less agitated according to the weather. So the weather changes also impact on the soil, and is generating more or less signal or more or less noise on this frequency band. So we can see these changes on a diagram of 24-hour. Each line is 30 minutes. So we have a number of lines. We also have an earthquake here, and we have a changes. So at the beginning, maybe this is during the night, we have no strong signal. We have ambient noise, which is relatively low. We have some disturbances. These small spots are from car passing by the seismic station, etc. Other disturbances on the station. And then suddenly we can see an increase of the noise of the signal on the ground, on the surface of the Earth. And then we have an earthquake here. So these changes from this pattern to this pattern is because of the weather. The weather is changing, so the wind or the sea, which is become more agitated, reflects on the ground. This is important to know because using this type of signal, we can detect and, for example, use the signal to illuminate the morphology of the underground and make a seismic survey using the so-called passive methods. One of the most common passive method is the HVSR or Nakamura method, or others are seismic antenna like REMI. As I want to put in evidence what is the magnitude of this type of displacements. We can say that the seismometer can detect motion near to the nanometric scale. The passage of a vehicle on a road at a distance of about 1 kilometer generates something amplitude in the scale of the nanometer, so the thickness of a DNA chain. Microseismicity is generating vibrations in the sides of one blood cell, red blood cell of our blood, for example, one cell. So it's very small vibration. And the Earth tide, which also affect the planet, it's generating signal very long period, a period of 20 hours or more, in terms of centimeter, up to 30 centimeters. An earthquake magnitude 4, especially in the epicentral area, can generate signal of centimeters, and an earthquake of magnitude 7 can generate signal of meters. So what we are detecting, we are trying to detect from the ground, is something at the level of nanometric scale or micrometric scale. I think this is important to understand, to grasp what kind of type of vibration, very, very small vibration we can detect using and are generated by ambient noise. So this leads to a very important topic. Okay, we know more or less the amplitude of the signal on the ground, but what is the capability of detection of our instrumentation? It will become more clear later while I explain, but I put this diagram here, an example of 3 types of common sensors for vibration measurements. The first one in the top is a geophone. So it's a plot of a geophone. It's a plot of a signal detected by a geophone. This is a plot of the signal detected by a MEMS. This is a plot of the signal detected by a force balance accelerometer. What they have in common? What they have in common is that all these 3 sensors was placed on the same platform, on the same place, all the 3 together, all 3 connected to the same digitizer, obviously 3 different channels. So gathering the data, ambient noise on a platform, on a reference platform in our lab, we can show that there are some limits in the detection. So looking at this signal, you can see from the geophone, you can see that it detected some kind of signal. So we have a peak here, a peak kind of trend here, another peak here, something like here. And we had also the amplitude, that the frequency that is going down at this point at 1 Hertz, and going a little bit up here, and then going down again here. And these 2 curves that you see overimposed here, this green one and the purple one, these 2 curves are the noise model that I showed you before, the Peterson curves. And you can see that this small trend of going up of the signal here in this point, it's correspond and match to the possible ambient noise generated by the ocean, by the sea motion, which impact on the ground. So the geophone detected some of this motion that we expect to see. What about the force balance accelerometer? Well, the force balance accelerometer detected mostly everything as the same of the geophones. This signal is equal to 1, or is equal to this one. But if we go down to the frequency, we see that the force balance accelerometer became flat, or not going down as much as the geophone. And not going down, it could not going up again on this point, because it's less sensitive. So geophones are more sensitive than force balance accelerometer. On the other hand, opening and closing a parenthesis, of course, the force balance accelerometer can accept very large shock without clipping, without saturating the signal, things that geophones cannot do. So the geophone cannot be used for strong motion, but very well for weak motion. But what about the MEMS sensor? So this is one of the MEMS sensor most widely used on the market recently. And a lot of manufacturers are using this MEMS sensor. I don't tell you the brand, I don't tell you the part number of the component, because it's not this the scope of this. I don't want to make a comparison with the, let's say, competitors. But the point is, you have to understand the limit of detection of your sensors. This is a not bad sensor. It's a quite good sensor. It can detect acceleration quite well down to 0.1 millig. So, but if we put this sensor on the same platform together with two other sensitive sensors, we can see the limit. So this straight line, it's just noise of the MEMS sensor. So we are completely blind below this level. So if we have a signal in a building, in the soil, wherever you want, which is lower than this threshold, that MEMS sensor will not detect anything. This is the most important thing. So you have to use the proper sensor in the proper application. How we can claim that geophones can be very sensitive and have a high capability of detection? We put on the same platform two geophones. These are triaxial geophones of our production. We connected these geophones to a digitizer. We recorded some signal. We deconvolved the signal to displacement, because when you deconvolve to displacement, you have the best way to detect the quality of your signal. We limited a little bit the band in this case, but you can see that the two signals, especially this portion of the signal, so these two are from one sensor, these two are from another sensor. This second track is the zoom of this portion. This second track is the zoom of this portion. And even if the signal is not exactly the same, but they are really very, very similar. So you can see here the signal is almost identical. There are some other places which is not so identical, like this point is not exactly identical here. So it's a demonstration there are two different sensors, which has some limits in the detection. But you can see here, this number here is 47 nanometer in this point of the diagram. 47 nanometers. So we can say proportionally that this peak is about 12 nanometers. And this small peak here is probably less than 8 nanometers. And both of them detected the signal. So we can say that the displacement of detected by these two geophones is in the range of the nanometers in this frequency range, which is about from 0.5 to 8 hertz about. So we can say that absolutely, we can be absolutely sure that the signal detected by the signal here detected by the geophone is real. It's not a fake, it's not an artificial signal generated by the electronic, but it is exactly a real seismic signal, because both of them detected the same signal. So the same methodology can be used for any other sensor. So if you want to test the quality of your system, you can put 2 or 3 or more sensors together and record the ambient noise and use the ambient noise as a reference tool for your instrumentation. This can be very important, for example, when you want to measure vibration of this type of buildings. This is a very old bridge. It's a bridge on a railroad near our city, near Perugia. It's made of bricks. This bridge is very old. It has some damages. So the authorities wanted to detect the vibration on this bridge when a train passes over, etc. And that occasion was an occasion where the geophones could make absolutely a good job. And is an occasion of an application which the MEMS sensor will not make any good job. In this case, finally the company started force balance accelerometer in this bridge because they wanted to see very weak signal, but also they are concerned about strong motion because this bridge is near a highly seismic area. So they decided to install force balance accelerometer, and what was a good choice. So this is more or less closing, I think, a very important chapter of the signal to noise ratio evaluation. After this, I want to show you as an example of a much more complex installation. Is a structure health monitoring system in the hospital in Ancona. This building is rather old and has been reinforced recently. This is from the map. There are several branches of this hospital. Each segment of this branch is divided in 2. You will see later on the diagram. And the reinforcement, you can see this is a grid, 1, 2, 3, 4. There are towers. It has been raised up to keep more steady the vibration on this direction. And so after installation of these reinforcements, the University of Politecnica delle Marche, Professor Fabrizio Gara, wanted to install a monitoring system. So a monitoring system monitoring system. And this is a detail of the reinforcement on this hospital. There are a kind of dampers here because this tower is connected to the wall, to the main wall, and there are dampers here. And they wanted to see the behavior of this reinforcement. The hospital has been equipped with all these accelerometers. You can see the segment was divided in 2, and so there's a junction here, and so the tower, reinforcement tower, and 1, 2, 3, 4, 5, 6 accelerometer. Here there's one recorder, other accelerometer, one other recorder, etc. And so all of these all of these accelerometer go straight to a number of recorders. And these recorders, so this one recorders, taking the signal from the force balance accelerometer. So this group of sensors go to this recorder, this group of sensors go to this recorder, etc. And this is at the 7th floor. All these sensors are at the 7th floor. They go together to each set of sensors go to one recorder, and all the recorders are synchronized by the central station, which generate a GPS signal propagated over the LAN cable. So it's a precise synchronization between all the sensors. And this, you can see here 2 of the many accelerometers that they have. And in the basement, there is a sensor to give the seismic input in case of earthquake, and these are also accelerometer may put on the reinforcement. I scroll up again. So that accelerometer are below this platform, in between this platform. These accelerometers are in between this platform. So everything together is collecting data, and these are pictures of the accelerometer. One on the one side and on another side, in the two sides of a junction box, junction point of the building. There is a junction here, and so they can detect very well the mode of resonance of the building because they are using force balance accelerometer. In this case, even in this case, MEMS will not give a good result in our opinion. So this is mostly the end of my presentation. So maybe we can give space to question and answers, possible answer if I can be capable to answer your questions.
Muy bien, pues esta ha sido la presentación de Mauro. Él comenta que si hay alguna duda nos la hagan llegar en el chat de nuestras respectivas plataformas de redes sociales para que podamos darle salida a sus inquietudes y preguntas.
Yes, Mauro, we are waiting for questions from the viewers. So it's a very interesting presentation. Particularly, this installation in the bottom of the sea is very complex installation. Leo has a question about the concrete of the.
Sí, porque yo quería saber este bloque de concreto simplemente se dejó en el fondo marino sin ningún tipo de sujeción.
Leo is asking, the concrete block in your installation just put in the sea and then the block lie on the bed sea, or you make some anchor between the floor sea and the concrete block?
No sé si nos pudo escuchar Mauro, si pudo escuchar nuestra inquietud.
Pues, sí, desmontaste.
No se escucha.
Can you hear me now?
Questions from our viewers. In this moment, Leo has a question about your installation in the sea. He's asking about the block, the concrete block. You only drop the concrete block in the sea, or you anchor the block to the floor sea with something?
No, the block it was rather big and heavy. So it was big and heavy also because we don't want to make any operation under the seabed. So deploying a very heavy and massive block, it will just lay down and give us more confidence that the ocean currents, etc., will not disturb too much. And in fact, we had very good results.
Okay, thanks. I have a question about this installation. If you can share us, if you can, obviously, how much money approximately cost this type of installations?
Well, honestly, I don't know. I know the cost of the sensors and of course the cost of the cable, etc. But since the installation was carried by a system integrator, our partner in Turkey, Sentets, I don't know the final cost of the installation, but I can maybe I can provide to you more details in the next days. I don't remember, not remember. I don't know exactly what is the cost of the installation itself. But of course, with the boat, with the marine equipment, and the buoy, the buoy is quite expensive. I think but take my words with all the caution. I think the buoy is in the range of the 20,000, and the equipment is in the range of the 20,000. So I don't know what is the cost of the boat, but I think each installation will be in the range of the probably 60,000.
Okay, thank you. ¿Tenemos más preguntas en los chats?
¿Alguna pregunta? Parece que no tenemos preguntas por parte del público. Si hay algo en lo que quieran que se redunde acerca de la información que ha mostrado Mauro, nos pueden comentar para redundar. De la misma manera, si es necesario que nosotros lo platiquemos también en español para un mejor entendimiento, también pueden comentarnos, por favor. Digamos, otra pregunta. De acuerdo entonces a lo que, y no sé si podrías abrir el micrófono para que Mauro nos escuche.
Sí.
De acuerdo con lo que nos mostró Mauro, en estas diferentes gráficas en donde tenemos la relación señal-ruido, ¿qué equipos él recomienda entonces que utilicemos para, por ejemplo, la vibración ambiental? Sobre todo la que es más utilizada, que es para la zonificación sísmica y que son mediciones que se hacen sobre el suelo. ¿Podrías preguntar?
Sí, claro. Mauro, we have a question about, you talk about noise and signal plots. What do you equipment recommend for ambiental vibration, particularly this with the objective to make a sonification soil?
Yes, for the zonification or micro zonification, it's very important to recognize that or to verify that the sensor we are using is detecting properly the ambient noise, because only if it detects properly the ambient noise, we can have the confidence that the signal as ambient noise or ambient signal, we can say, has transported information on the subsoil and give us the information on how the soil is behaving, how the soil is vibrating. To recognize this, I can, if you like, I can try to share one of the processing model that we have for HVSR. Recently, we introduced also the plot of the noise curves on the HVSR processing model, exactly to help people to recognize what is the good signal and what is eventually a bad signal. If you do you want, I try to show this.
Yes, absolutely, no problem. We have another question, Mauro.
Yeah. Yes.
This is a question from our partner, Marco Rubio. There is a deep limit to place submarine devices. If not, you have made some tested on continental tectonic lakes?
Sorry, can you repeat, please?
Sure. The question is, there is a deep limit to place submarine devices. If not, you have made some tests on continental tectonic lakes?
You mean the seabed seismometer?
Yes, sir.
Okay. Well, using the umbilical cord, at least for the technology that we can offer in this moment, we see a theoretical limit now in this moment with the sealing devices and the type of cable we have. It's about 500 meters. We don't have experience in deploying other, because these are our first installation. We deployed it successfully and we are very happy, but we cannot say we are the most expert. We have to be humble. But it was a good opportunity. In this case, the maximum depth is 45 meters, but the limit for the technology that we have used is 500 meters.
Okay, thanks. We have another question from Daniel Ruiz. He's asking, what differences in instrumentation must be taken into account in historical buildings for structural health monitoring?
Yeah. Historical buildings are often made of stones, not concrete, not steel, in some cases wood. So wood, there is no problem. In wood, you may use even MEMS sensor because wood vibrates a lot. If you have steel-made buildings, also they vibrates quite a lot, so MEMS sensor could be used. But for historical buildings where large blocks are used, stone blocks, I mean blocks of granite or blocks of any type of stones, you will have basically very stiff structures. They don't vibrate much. They vibrate mostly from the ground, from the vibration of the ground that you see as very small. So my recommendation is to use the seismometers. Geophones are kind of seismometers. So geophones are very, very good for this application. Of course, the geophone must be connected to good quality digitizer. Else you cannot obtain these high good results that we obtain, because we improve the resolution of the digitizer very, very much.
Okay, thanks, Mauro. We have any question or comments, Gio? Well, Mauro, there is no more questions by the moment, but if our viewers later a question, please send us via email, and we will return to Mauro. Mauro, thanks a lot. Engineer Pita wants to say something.
Yes.
Hola, Mauro, muchas gracias por tu plática muy interesante. A todos los que nos acompañaron también en esta transmisión de Expert. Sin duda que SARA ha permeado ya en el mercado mexicano de la exploración, en la salud estructural, de edificaciones, y son propuestas tecnológicas de muy buena resolución y compiten en precio muy bien con la tecnología tradicional. Es decir, SARA está liderando en el mercado nacional ya a través de Geotem como aliado representante de SARA. Digamos, en el último semestre hemos vendido más de unos 50, 60 acelerómetros, equipos de exploración, como son sondas para pozo, en fin, creo que los ingenieros dedicados a la exploración de subsuelo se han dado cuenta que la propuesta tecnológica de SARA pues tiene ventajas tecnológicas y en costos, por supuesto, también. Bueno, pues gracias, Mauro, y a todos por participar en esta reunión técnica. Saludos.
You're welcome. I thank you very much for this opportunity.
Thank you, Mauro.
I'm sorry for the inconvenience at the beginning, but something happens. This is the.
Don't worry, Mauro. It's part of the show.
It's part of the risk. Okay.
Pues, en contacto directamente con Mauro acerca de cualquier tema relacionado con esta plática y acerca de lo que él ha comentado.
Justo, perdón, Leo, hay una pregunta más de Daniel Ruiz. Question, Mauro, is what is the future of for technological improvements?
What is the future for the technological improvements?
Yes.
It's hard to say. Well, there is some interest in terms of vibrations analysis. There is some interest in the last period of time regarding the use of fiber optics. Fiber optics is a kind of so-called distributed acoustic systems or distributed acquisition system. It's in what I have understood until now, it's interesting because you can detect vibrations on a larger scale, maybe using existing infrastructures like fiber optics for internet or fiber optics for telephony or anyway communication equipment. So you can mix up communication infrastructures with vibration measurements. What is not clear until now, or not clear to me, is the capability of fiber optics to detect or to quantify the vibrations. Because if you are considering many transducers for vibrations, we count on them to give us precise measurement of the translation of the vibration. So in three axes. Another interesting development maybe in the next future, which are not in this moment, they are not so it's not often used, rarely used. It's rotational seismometers. There will be probably in the next 10 years, we will see more use of rotational seismometers. So to detect the torsion of points. In this moment, I don't have in mind something specific, but and of course, it will be the capability of artificial intelligence to analyze the signals. This will be surely development that will take place in the next probably 5 or 10 years, maybe 5, not 10, because the AI is going to be to have a key role in the data processing in the next year.
Yeah, absolutely agree with you. The intelligence, artificial intelligence, it's the more than tomorrow. It's today an important key to develop a lot of new algorithms. In this case, to automatic processing seismic data.
Yep. Yes.
Muy bien, pues muchas gracias, Mauro. Seguro tendríamos muchas cosas más que platicar acerca de los diferentes equipos y detallar muchas cosas más, pero el tiempo nos limita un poco el tiempo que tenemos aquí en este espacio. Agradecemos también a los que han estado conectados y gracias por la paciencia y por seguirnos a través de esta transmisión que ha sido un tanto particular el día de hoy, porque ha sido una transmisión en inglés con títulos que nos ofrece la misma plataforma de Meet, que es a través de la que nos conectamos con Mauro. Agradecemos también al ingeniero Carlos Pita que nos haya acompañado y que nos haya retroalimentado con sus comentarios. Recuerden que Geotem es representante en México de Geo y de los equipos Geo, de tal manera que si hay alguna inquietud que ustedes tengan relacionada con estos equipos, también pudieran contactarnos para que platiquemos y resolvamos sus inquietudes. Los quiero invitar para que sigan nuestras redes sociales, en Facebook, en Instagram, en YouTube, nuestro canal de YouTube y nuestras diferentes redes sociales que habilitamos para que ustedes tengan la información que luego transmitimos, incluso esta misma conferencia que luego se sube a nuestros canales de redes sociales. E invitarlos para que nos acompañen en la próxima entrega el próximo mes, que será, como saben, el último jueves del mes de agosto, que caerá 29 de agosto, en donde tendremos un invitado muy especial como sorpresa. Así es que los invitamos para el siguiente mes. Quiero agradecer también a Eliu que me haya acompañado el día de hoy y ayudarme a transferir las inquietudes del público a Mauro, quien él conoce muy bien y ha estado muy en contacto y colaborando con Eliu y Eliu con Mauro en los diferentes proyectos que estamos realizando actualmente en Geotem. Y agradecer también aquí detrás de cámaras a Giovanni Mendoza por sus aportaciones a la tecnología aquí para que nosotros podamos transmitir esta conferencia el día de hoy. Pues le doy las gracias de nuevo. Yo soy Leonardo Veras y con esto cerramos la conferencia Experts del día de hoy. Muchas gracias.
Gracias.
Pasen buena tarde.
Gracias.